Okay, hi everyone. Thanks for coming to the Graphs of Matroids seminar. Today we have Ahmad Abdi from LSE, who's going to be talking about packing dijoins and digraphs and weighted digraphs. Go ahead, Ahmad.
Thank you, Shayla, for the introduction, and thanks for having me. Yes, so I'll be talking about packing dijoins and digraphs and weighted digraphs, and this is based on joint work with Gerard Cornijols and Michael Zlatan from Carnegie Mellon University over the past couple of years. The work I'll be talking about is based on a paper of the same title that appears on the archive. And the paper addresses two conjectures in combinatorial optimization, known as Whittle's conjecture and the refuted Edmonds-Giles conjecture. And to tell you what these conjectures are about, I need to set up some terminology. So we're given a directed graph on vertex set V and arc set A. A die cut is a subset of the form delta plus of U, where delta minus of U is empty. In other words, it consists of the arcs going from left to right in a partition of the node set into two sets, where all the arcs go in the same direction. And why are die cuts relevant? They're relevant in the context of strong connectivity of directed graphs. You can see immediately that if you have a die cut, then the graph is not going to be strongly connected because there is no directed path from a vertex on the right to a vertex on the left. And you can show the converse of this is true in some sense. If your graph is not strongly connected, it's because there is a die cut. Okay, so note the requirement that the shore is non-empty and not the whole vertex set. There's a blocking notion to die cuts, and so an arc set J is called a dijoin if contracting the arc set makes the digraph strongly connected. Now, you can see that if J is a dijoin, it has to intersect every die cut at least once, because if it doesn't intersect a die cut, then even after you contract the arc set, the die cut remains alive in the contraction, and therefore your graph won't be strongly connected. So if you have a dijoin, your dijoin better intersect every die cut at least once. And you can show that the converse of this statement is also true, that if J intersects every die cut at least once, then it must be a dijoin. That's a nice exercise. So there's a blocking relation between die cuts and dijoins. So because of that, you can ask questions about, you could ask packing and covering questions about die cuts and dijoins. What is the maximum number of pairwise disjoint die cuts that you can find in your digraph? What is the maximum number of pairwise disjoint dijoins? And if you're packing, the first problem is known as a die cut packing problem. The second one as a dijoint packing problem. And so we could actually define things in a more general framework, in a weighted framework. So we're given weights on the arcs. We ask that the weights be non-negative and integer. A W-weighted packing of die cuts of value nu is an assignment of non-negative integers to the die cuts, so that the sum of the values is nu, and the congestion at every edge is bounded above by the weight of the edge. So in other words, the sum of the values of the die cuts that contain that edge, A, is bounded above by WA. Okay, so if you're focusing on the weights equals 1 case, then Y can be interpreted as a packing of pairwise disjoint die cuts. All right, packing of new pairwise disjoint die cuts. Okay, now you can ask what is the maximum value of a weighted packing of die cuts, and it turns out that every die join can give you an upper bound on this value. More specifically, the weight of any die join, the W weight of any die join is an upper bound on the maximum value of a weighted packing of die cuts, whereby the weight of a die join, what I'm referring to is the sum of the weights of the arcs inside the die join. Okay, and the reason why this is true is because of weak linear programming duality. What you can do is you can set this up. You can set up this problem as a maximization linear program, where your linear integer program, where your constraints, your resource constraints look like this. The variables y are asked to be non-negative and integer, and you want to maximize this objective function. Okay. Now what you can do is you could relax the integrality condition, move to the dual LP, and then reimpose integrality condition on the dual LP, and the dual LP is precisely solving the dual integer LP is precisely solving this problem, minimum weight of a die join. So that's the connection. So you can get this inequality between the two. And Lucchesi and Younger proved that you actually have equality here, that the minimum weight of a die join is always equal to the maximum value of a weighted packing of die cuts. And this is an important result in combinatorial optimization, because it has led to deep research in the area. In particular, this min-max relation was somewhat responsible for the theory of submodular flows, and that's just one of the things that it prompted. Okay, so here you could actually you don't need to work in the weighted setting. It suffices to prove this result for the all ones weight. And this is because you could simulate weights by uniform weights as follows. If you have an arc of weight WA, you could replace it by a directed path of length WA, where all the weights are equal to 1. And if you have a 0 weight arc, you could simulate that by just contracting the arc. And so by doing this, you could just translate the problem of finding a maximum value weighted packing of die cuts to one of finding the maximum number of pairwise disjoint die cuts, basically. So we consider this problem solved because we're just interested in the min-max relation and not the algorithmic aspects at this point. So now what we do is we swap the role of die cuts with dijoins, and we ask the same question. Okay, so now you could define a weighted packing of dijoin in a similar way, where this time we're assigning non-negative integer values to the dijoins, and you could ask for the maximum value of a weighted packing of dijoins. And we will call that nu of d comma w. And again, there will be a dual parameter, namely the minimum weight of a die cut, and we'll call that tau of d comma w. And again, you can imply a weak LP duality to get this relation between the two. Tau will always be an upper bound on nu. Edmonds and Giles, after the result of Lucchesi and Younger, Edmonds and Giles conjectured an inequality here as well. And just a few, before I tell you, this conjecture has now been, was refuted just 3 years after that. But before I tell you about the counterexample, let me tell you about a strange phenomenon that happens here. So, as I said, the Lucchesi-Younger theorem, it was sufficient to prove that for the all ones weight. Can we do a similar thing here? Can we say that it suffices to prove the Edmonds-Giles conjecture for the all ones weight? Well, you can try. You can say that if I have an arc of weight WA, weight at least 1, you could replace this by WA many parallel arcs. Okay, and this will be completely fine. But a problem arises when the weight of an arc is 0. The natural thing to do here would be to delete the arc. But this causes an issue. Does anybody see what the issue here is? So I'll tell you myself. So what's happening here, when we apply these operations, we want to make sure that the tau and nu parameters change as we expect them to change. Actually, we don't want them to change at all. But what happens is when you remove an arc here, you can create new die cuts. So now all of a sudden, you could actually create a cut of a die cut of this form, which would not have been a die cut in the original digraph. So this will be a new die cut. And this can create issues because when you remove the arc, you create this new die cut. This could, you no longer have control over the minimum size of a die cut. You no longer have control over tau. So if this new die cut is very small compared to the original tau, it's going to change the left-hand side drastically. So you will no longer be able to pack as many die cuts as yet set up to do. So this causes an issue. So the answer to this question is that no, it doesn't suffice to prove this conjecture for W equals the all ones vector. But this operation does tell us that it suffices to prove the conjecture for 0, 1 weights. So suffices to prove this for 0, 1 weights. Unfortunately, for 0, 1 weights, the conjecture is not true, and this was shown by Scriver just 3 years later. And in fact, he showed that the conjecture isn't true even if tau is equal to 2. So even if you have to just find two disjoint dijoins among your weight 1 arcs, you might not necessarily be able to do that. So the example is as follows. We're given these 2 hexagons connected as you see in the picture. The black arcs, the solid arcs, have weight 1, and the dashed arcs have weight 0. So you can see that the solid arcs form 3 paths, 3 pairwise vertex disjoint paths. Okay, and this instance does not have this 2 disjoint dijoins. Now remember, we're looking for a weighted packing of dijoins. So dijoins cannot use weight 0 arcs because the congestion for the weight 0 arcs is 0. The tolerance is 0. So if you did have 2 disjoint dijoins, it would have to use the black arcs. Okay. Now, one thing I want you to note is that these nodes, the inner nodes of the paths, are sources and sinks. This and this, this and this. All right. So they give rise to die cuts, trivial die cuts. Now, every dijoin will have to pick at least, if you have 2 disjoint dijoins, you have to distribute these 2 edges evenly to the 2 dijoins. So if you did have 2 disjoint dijoins, it's going to lead to a 2 coloring, a sort of 2 coloring of the 3 paths. So here I've given one such 2 coloring, where the green arcs correspond to one potential dijoin, the red arcs correspond to another potential dijoin. But then no matter how you do this, you're going to come up with the so-called monochromatic die cut. So if you look at this now, if you look at this forms a die cut. All the arcs are going from right to left, but all the arcs crossing are green and you don't have any red cuts. Now you could try to shuffle the colors around and change them, but you will get a problem with either this other die cut or this die cut, or there will also be another die cut that will separate the inner hexagon from the outer hexagon. So this simple example tells you that the Edmonds-Giles conjecture is just not true. Okay. Any questions before I proceed? Okay. So there's actually an extension of this counterexample to all taus. So the previous one was just for tau equals to 2. You could extend it to a counterexample for any tau by simply replacing the weight of this arc, and this arc by tau minus 1. So instead of the original weight was 1, now we'll replace the weight to be tau minus 1. And all the other weights remain the same as before. And here you can again show that the minimum weight of a die cut is precisely tau, and but you do not have tau. You do not have a weighted packing of dijoins of value tau. This was shown very nicely by Harvey, Kirali, and Lau. Just 10 years ago, 11 years ago. Okay, and this will be useful for us. All right. Despite this, Woodall has conjectured that the conjecture remains true in the unweighted case. So if W is 1, the L1's vector, then the minimum size of a die cut should be equal to the maximum number of disjoint, pairwise disjoint dijoins. And there's been quite a bit of work on this. So here I've sampled some of it. So for example, Frank and Tardosh formulated this problem as a common base packing problem for 2 matroids early on. Scriver and also Fiolofov and Younger proved the conjecture for source sync connected digraphs. I should say digraphs. And source connected digraphs are digraphs where you can get from any source, any sink to any source by a directed path. Lee and Wakabayashi proved the conjecture for series parallel digraphs. These are digraphs whose undirected versions are series parallel. And then this was later extended by Lee and Williams to digraphs whose underlying graph has no K5 minus an edge minor. And recently, Misharos proved the conjecture for digraphs whose underlying graph is so-called Q-1, partition connected for Q prime power. Now, this notion I can tell you at the end of the talk if you're interested in this, but this relates to Nash-Williams's theorem for packing spanning trees. And here already you can see that there is a connection to number theory popping up. Okay, we'll see this aspect of it in our talk today. And there are many results that I didn't mention, but there's other interesting results by Kornijals and Gunan, Shepard and Veta, and also recently by Chudnovsky, Edwards, Kim, Scott, and Seaman. Okay, we'll see connections to this paper and also this paper at a very high level. And this paper is lurking in the background, but we'll also phrase our problem as a common base packing problem for two matroids. But this is done in an entirely different way than the way it was done for Frank and Tardosh. One thing I should mention is these results 2 through 4 are true more generally in the weighted setting. So these 2 through 4 are true also in the weighted case. Yeah. Okay, so that's so I'm just doing my due diligence by giving you some context. Now, on to our results. So we have 4 what we call principal results, and we have a bunch of other secondary results in the paper. I plan to tell you about these principal results and give you a flavor of what's going on in the background and how we get these results. And the hope is that the techniques we develop and the approach we develop will hopefully lead to a resolution or refutation of Woodall's conjecture, and also a fixing of the Edmonds-Giles conjecture. Okay, so for the first one, I need to tell you what a K-dijoin is. So I'll say a subset of arcs is a K-dijoin if it intersects every die cut at least K times. Okay, one example of a K-dijoin is if you give me K pairwise disjoint dijoins and you take their union, that will give you a K-dijoin. That's one way to get a K-dijoin. There are other ways to get a K-dijoin, okay, that don't necessarily correspond to the union of K pairwise disjoint dijoins. And what we show is in the unweighted setting, you can partition the arcs into a dijoin and a tau-1 dijoin. Okay, so if you want to prove Woodall's conjecture, this tells you how to pick the first dijoin, because it tells you have enough room left to find tau-1 other dijoins. Why doesn't this already prove the conjecture? It's because of the phenomenon with the weights. Setting weights to 0 is not the same as deleting arcs. This result is tight in the sense that it doesn't extend to all weights. Okay. Scriver's example, counterexample, tells you why, right? If you look at 0, 1 weights, there you have an example where tau is 2 and you can't find 2 disjoint dijoins among the weight 1 arcs. So this is tight in that sense. And obviously it extends to all non-zero weights, weights with no non-zero entry. Okay, to tell you about the other results now, here the number theoretic aspect is going to kick in a different way than the paper by Messaros. What we're going to do is, so we have our digraph, all right, and we're given tau, which you can think of as a lower bound on the weight of every die cut. Okay. For every vertex V, we're going to look at the total weight of the outgoing arcs minus the total weight of the incoming arcs. And we'll look at that value modulo tau. All right, that's going to bring the number to somewhere between 0 and tau minus 1. Okay, and we call that M sub V. So if you look at Scriver's example, for example, here, for tau equals to 2, here you're going to have 0 because the right-hand side is just 2. All right, and 2 mod 2 is 0. Here you're going to have 0 minus 1, which is going to be 1 modulo 2. And you can do this for all the numbers. Then what we do is we sum up these values and we divide it by tau. Okay. When you sum up these values, you're bound to get something that's divisible by tau, because over here the right-hand side is 0. If you add up all the right-hand sides over the reals, it's going to give you 0. So you could use that to prove that the sum of MVs is always divisible by tau. And we normalize that, we divide it by tau, and that's what we call rho of tau dw. Okay, so in this example, in Scriver's example, you could sum up all the numbers. You're going to get 1 over 2 multiplied by 6, and that's 3. Okay. And this 3 is sort of the barrier we try to push, actually. It turns out to be the barrier. This is where strong base orderability kicks in. All right. One more thing was, say a weighted packing of dijoins is equitable if for any 2 dijoins that you use in your packing and any inclusion-wise minimal die cut, the number of arcs that the first dijoin picks up is roughly the same as the number of arcs that the second dijoin picks up. So the difference in the intersections is either 0, 1, or minus 1. Okay. Now I can tell you about the second principal result. And the result says that if this rho parameter is bounded above by 1, so that it's 0 or 1, then you will always have an equitable weighted packing of dijoins of value tau. So not only does Woodall's conjecture hold in this case, actually Edmonds-Giles holds in this case. And it actually holds in a very strong sense. You can find an equitable weighted packing of dijoins. And this result is also tight in a sense. It doesn't extend to rho equals to 2, even if all the weights are 1. And the example is just a simple instance here of indicated what the MVs are. Rho is 2. And here tau is 2, rho is 2, and we do not have an equitable packing of 2 dijoins. Let me just give you an example of why this may not be equitable. So here I've indicated 2 dijoins in this instance. So as you can see, every source and sink is incident with a blue edge as well as a red edge. And if you look very closely, you will find a die cut here that disproves equitability. So I need to spot it myself. Yeah, so here, if you look at this, here we have a die cut where all the arcs, so all the arcs are going the same direction. The blue edges, there are 3 blue edges. There is only 1 red edge, and the difference is 2. So it's not 1. So this is not equitable. And you can show that's the case for any packing of 2 dijoins in this instance. So this second result also doesn't extend to rho equals to 2. However, if rho is equal to 2, there is a weighted packing of dijoins of value tau. So we prove this to be the case. This is true. And again, this is tight. This doesn't extend to rho equals 3. And the example, the counterexample, is that the extension of Scriber's counterexample. So if you look at that extension where the middle arcs of the paths have weight tau minus 1, rho will be exactly 3. You can rho with respect to tau will be 3. And here, as I said, this example doesn't have tau disjoint dijoins, weighted packing of tau dijoins. So this result also doesn't extend. Okay. Now the final result we have is for the case where rho is equal to 3. Now, as I said, when rho is 3, there's no hope to get this result. But what if the weights are 1? Okay. There we have Woodall's conjecture, right? And we prove that that is indeed true. So if the weights are 1, tau is 3, and rho is 3, then you can indeed partition A into 3 dijoins. And this requires heavy machinery, basically heavy machinery from combinatorial optimization, matroid optimization, as well as matroid theory. And this result is also tight. It extends, while it extends to all W strictly positive, it doesn't extend to all weights. And again, it's just the previous counterexample, but with tau equals 3. Okay. So basically, all the results are pushing the barrier in different directions. Okay. How do we, so this talk just focuses on uniform weights. However, several results extend to all weights. What is the outline of the paper? So there's 5 stages to all the proofs. All the proofs are they're not disjoint proofs. They actually follow. There's a certain spine, and everything is following that spine. So it's quite linear. So in the first stage, what we do is we reduce the problem of packing dijoins, and more generally K dijoins, to one on so-called sync regular tau plus 1 bipartite digraphs. So what are these things? These are just nearly tau regular bipartite graphs. I'll say a bit more about that in a bit. So that's basically the first stage. We translate all of the problems to this, and this works in both the weighted setting and the unweighted setting. Then in the second stage, we introduce objects called rounded one factors, and these are very much like perfect matchings in bipartite graphs. And we interpret Woodall's conjecture as a problem of packing certain rounded one factors in bipartite graphs, and from there prove the second principal result. In the third stage, we go further. From there, we introduce a matroid M1 on the vertex set of the bipartite graph. And we use matroid optimization, in particular results of Fujishige, Franken, Tardosh, and Edmonds on crossing submodular functions to prove the first principal result. In the fourth stage, we introduce another matroid M0 on the same ground set, And then we connect Whittle's conjecture to packing common bases of the two matroids M0 and M1. And then we prove the third principal result. And in the final stage, we see that strong base orderability, and this already shows up in stage 3. Strong base orderability shows up. Because strong base orderability is linked to packing common bases of matroids. And so we use that to try to look for an MK4 free restriction of one of the two matroids, M1, and we use strong base orderability to prove the last principal result. Yeah, so MK4 is the cyclomatroid of K4. Okay. Even before the talk, I didn't expect to get to stages 3 and 4. I do have some slides, a few slides, if anybody's interested after the end of the talk. But yeah, stages 3 and 4, I won't get to talk much about it. But you see how what prompts stage 3 and 4. Any questions before I move on? Shayla, how much time do I have?
Maybe 15 minutes or so. We did start a bit late, so feel free to go all the way up to the end of the hour.
I think 50 minutes should be, well, let's see, 50 minutes. I try not to go over.
Okay.
Okay. So in the first stage, so this is the decompose, lift, and reduce procedure. What is the idea? And this is really the thing that initiated the entire work. So I give you a digraph D, where every die cut has size at least tau, and let's say tau is at least 2. That's the interesting case. The goal is to find tau destroying dijoins. And the idea is to lift, by lift I mean uncontract D to a tau regular or nearly tau regular bipartite graph or digraph. Bipartite graphs, you could interpret them as digraphs. You just orient all the edges from left to right in your bipartition. So that's the idea. Lift your digraph D to a tau regular or nearly tau regular bipartite digraph. Pack dijoins in that lifted digraph by using Hall's marriage theorem or something like that, and then project the packing back onto the original digraph. That's the whole idea. Okay. So how would we go about this? This is by using gadgets, okay? So give me an arbitrary vertex. What do I want to do? I want to replace this vertex V by a gadget. Ideally, I want every vertex in the gadget to be a sink or a source of degree tau, okay? Degree tau after you attach it to these original arcs. And I want every die cut of the new digraph to still have size at least tau. Okay, then what I do on the right side, I pack my dijoins, tau dijoins, and then I project them back in the original digraph. Okay, this sounds great, but there's some obstacles, but you can deal with the obstacles relatively easily. Okay, so the first obstacle is a modular condition, and this is where this number theoretic thing comes in. As I said, you want every vertex in here to have degree tau, right? But then what does that mean? That means that if you look at this set, the weight or the number of outgoing arcs minus the number of incoming arcs should be divisible by tau, which means that in terms of the original digraph, out degree minus in degree should be divisible by tau. But this is not necessarily possible, right? So that's the first obstacle. Out degree and in degree might not be the same modulo tau. All right. Another obstacle is if the vertex V is a cut vertex, okay? And the issue is with this second part. If this was a cut vertex, then when you look at this gadget, you have this cut here, and you're going to create this cut, which could potentially be a die cut of small size, smaller than tau. So this is another issue. If V was a cut vertex in the original digraph, this might not necessarily be possible. And then the third obstacle is the combinatorics of the problem. This is not necessarily possible if tau is equal to 2. But this is good because in the undirected setting, the conjecture is true for tau equals to 2. This is a folklore result. Yeah, so this is really not much of an issue. Okay. In the unweighted setting, this is also not an issue. You could actually do it for tau equals to 2. So there's these three obstacles. So we need to revise our goal. We're given that tau is at least 3. V is not a cut vertex, and we want to replace it by a gadget where every vertex is a sink of degree tau, or the source of degree tau or tau plus 1. All right. And every die cut has size at least tau. And now you could let M sub V be that parameter that I defined earlier, which is the number between 0 and tau minus 1 that's the same as out degree minus in degree minus tau. And you can show very easily that the number of sources of degree tau plus 1 in the gadget must be at least M sub V. So this is how it shows up. And what we show is that a gadget with exactly M sub V sources of degree tau plus 1 exists. And this is a suboptimal example of it for tau equals to 3. Actually, one row of this brick wall is enough, but yeah. And yeah, so you can do this. You could do it in the weighted setting as well. And you could do it in a planar preserving manner as well. And for tau equals to 3, you could actually throw in simplicity as well. So you could, this is quite a versatile and flexible procedure. And so that leads me to the procedure. Okay, what we do is we do, in the first stage, we decompose our digraph D into 2 connected blocks, DI. Then we'll lift each DI by replacing every vertex with the appropriate gadget. And this gives us a family of digraphs D prime I. And then we'll reduce the problem of packing dijoins, or more generally K dijoins, in D to the same problem in each one of those D prime I's. And that hence the decompose, lift, and reduce procedure. And this works in the weighted setting as well. Now, each one of these pieces, D prime I, is a so-called sync regular tau tau plus 1 bipartite digraph. I'll explain that in a bit. And the total number of sources of degree tau plus 1 is the sum of these MVs. And this is where that row parameter comes in. This is precisely tau times row of tau D all ones vector. Okay, so that's the end of the first stage. Now I need to tell you about what these pieces are. So it suffices to prove the conjecture, both Edmonds, Giles, and also Woodall's conjecture, just for these graphs, or the weighted extension of these graphs. So what is it? You can think of this as a bipartite graph where all the vertices on the right have degree tau, all the vertices on the left have degree tau or tau plus 1, and every die cut has size at least tau. What do I mean by every die cut? We have an undirected graph. Well, we could orient all the edges from left to right, and this gives you a directed graph. Okay, and then what I'm asking is every die cut here should have size at least tau. What are the die cuts in this graph? Well, you get the trivial die cuts. Every vertex is a source or a sink, so you get these trivial die cuts. There is a third type of die cut, which comes from vertex covers, okay? You could have cuts of this form, where all the arcs go in the same direction, right? And you can see that this comes from a vertex cover. If this is a die cut, this is a die cut if and only if This is a vertex cover. So you have this one-to-one correspondence between interesting die cuts and vertex covers. So this is a vertex cover. Or the complement is a stable. Okay. Now let's see what Woodall's conjecture is guessing. All right. So we have these degree tau plus 1 vertices. Okay. This is what's stopping the graph from being regular. We call these vertices active vertices, and they're all sources. Okay. Now suppose Woodall's conjecture is true. So you have tau disjoint dijoins. What can you say about these dijoins that you're using in your packing? Well, a simple argument tells you that that every Ji intersects every vertex once or twice. And if it intersects a vertex twice, that vertex better have degree tau plus 1. Okay, because every vertex needs to give an edge, at least one edge to the Jis. Okay, and because every edge is incident with a vertex with a sink of degree tau, that tells you that the Jis must partition the arcs. Okay. And so in this instance, for example, one candidate would be this, and the complement of this would be another one. All right, and you can see that this satisfies the both J1 and J2 satisfy the degree conventions. And this leads me to the notion of a rounded one factor. A rounded one factor is an arc set J such that J intersection delta V is the degree of the vertex divided by tau rounded up or down. This is 1 or 2. Okay, and it's 2, it can only be 2 if the vertex has degree tau plus 1. Okay. So these rounded one factors, they look like this. They saturate every vertex, okay? And they have some degree 2 nodes. Okay. And now you can apply this classical result of Dewera from 1971. And it tells you that you can decompose your arcs in a bipartite graph. You can decompose them into tau rounded one factors. Okay, and you can show fairly easily that if rho is at most 1, this is an equitable packing of dijoins. That each Ji is actually a dijoin. And this argument also works in the weighted setting. So that's that second principal result. Okay. I'm gonna need just 4 or 5 more minutes, and then I'll stop. So the second stage, this is now basically you want to extend this result to larger rho, but there's a key issue here that you need to address. When are these rounded one factors dijoins? You need we haven't talked about that at all. Okay, so that leads to this question: when is a rounded one factor a dijoin? Okay, and so I just need to set up some terminology for a vertex set U. I define the discrepancy of U to be the number of sinks in U minus the number of sources. And for a vertex set U, I denote by A of U the set of active sources in U. Okay. One thing I want you to note is that discrepancy as a function is a modular function. So it's both supermodular and submodular. Now, how are these relevant? For example, you can easily show a double counting argument tells you the number of active nodes in your bipartite graph is precisely tau times the discrepancy. And this discrepancy is also precisely rho. This is also rho tau d. And you could also describe the size of a die cut in terms of its discrepancy in the number of active nodes. And this is, again, a simple double counting argument. The size of every die cut is precisely the number of active nodes in U minus tau times the discrepancy of U. These are simple double counting arguments. Now, when is a rounded one factor a dijoint? Well, we need to look at the dyad centers. So these things I call dyad centers. And let's collect those and call that Q for a fixed J. Okay. Now, what you can show is that the number of dyad centers is precisely the discrepancy. So this picks up precisely 1/tau of the total number of active nodes. And the intersection between every die cut and J is actually just a function of the vertex set to U itself. It's going to be Q intersection A of U minus the discrepancy. But this is a crucial fact. What this is saying is J is a dijoint if and only if this inequality is satisfied for every die cut. So for J to be a dijoint, J being a dijoint is solely a function of Q, the dyad centers. It's not a function of J itself. So what we're going to do is we're going to collect all these potential dyad centers. So we collect all the Qs, which have the right size, and satisfy that inequality. We haven't picked the dijoints yet. We collect those into a set, we call that B. This is where matroid optimization kicks in. You could use the right-hand side here is a submodular, supermodular function, in particular modular. You could apply a result of Fujishige to prove that B is non-empty. You could apply a result of Frank and Tardosh to prove that actually this is the set of bases of a matroid, which we call M1 over ground set A of V. And then you could apply Edmonds' results on base coverings, or the integer decomposition property of base polyhedra, to argue that you can actually partition the active nodes into tau bases of M1. And so this is a key lemma. And this is how you decompose into a dijoint and a tau minus 1 dijoint. You take this packing of disjoint bases, okay? You define an appropriate B vector, okay? And then that inequality tells us Hall's condition is satisfied. Actually, you don't even need the 1 plus. It tells you Hall's condition is satisfied, which tells you in turn that there exists a perfect B matching, okay, which is a vector defined on the arcs where x of delta v is just BV. And what does this mean? This is essentially saying that, let me scroll to the end. It's basically saying that there exists a rounded one factor J1 with dyad centers Q1. That's what it's saying. So it's saying, if you give me disjoint bases Q1 through Q tau, you must have a rounded one factor with dyad centers Q1. Moreover, this J1 is a dijoint. All right, so that's the dijoint. What is the tau minus 1 dijoint? It's just a complement. A minus J1 is a tau minus 1 dijoint. Why is that? Well, you just need to define your B prime vector appropriately and observe that the complement is also a perfect matching, perfect B prime matching. Okay. And then you can look at the intersection of A minus J1 with every die cut, delta plus U, and it turns out to be this expression, which is just the sum of U intersection QI minus the discrepancy. I going from 2 to tau. And each one of these terms is at least 1, because each QI is a basis. So you get tau minus 1. And then you can apply the DLR procedure to conclude this for all digraphs. So you give me any digraph where every die cut has size at least tau, you can partition the arcs into a dijoin and a tau minus 1 dijoin. Okay, so in other words, this tells you there's a dijoin so that when you remove it, every die cut still has the right, not remove it, when you set the weights to 0, every die cut still has a weight at least tau minus 1. So this is a good candidate for the first dijoin in a packing of size tau predicted by Waddell's conjecture. And but it's not always the right candidate. And here's an example where you can't decompose A minus J1 into 2 dijoins. And the example is very much like Scriver's example. Here you have the solid arcs form 3 paths, 3 disjoint paths. And all the inner nodes are sources and sinks. Actually, all the vertices are sources and sinks. So basically, if you do have 2 dijoins, it's going to give you a bicoloring of each one of these paths. And it can show that in any such bicoloring, one of the 4 die cuts that I've expressed here will be monochromatic. Okay. So how do you proceed further? Basically, the key notion to proceeding further is strong base orderability. Strong base orderability helps you in choosing Q1 and tells you how to decompose the tau minus 1 dijoin further. Okay, but I don't have time to tell you about that. I'm just going to finish with one very interesting open case, which shows an intriguing connection to Barnett's conjecture. The sort of simplest case where a conjecture is not known is the planar case, where tau is 3. You're given a planar digraph, every die cut is size at least 3, find me 3 disjoint dijoins. The DLR procedure allows you to assume that the digraph D is a planar 3,4 bipartite digraph. So this is an almost cubic planar bipartite graph. You can assume this. Okay. How do you proceed further? Here's a conjecture that we've made. Suppose you partition the ground set of M1 into 3 bases, Q1, Q2, Q3. We conjecture that there is a rounded 1 factor J with dyad centers Q3, so that when you remove it from your digraph, you're still connected. Okay, this conjecture, for those of you familiar with Barnett's conjecture, is very similar to that. In Barnett's conjecture, you're given a planar bipartite cubic graph satisfying some connectivity assumption, and you're looking for a perfect matching so that when you remove it, the graph remains connected. Or in other words, the graph is Hamiltonian. This is very much like that, except it's replacing the perfect matching by a rounded 1 factor. And why this conjecture? If you prove this, then you could use a result of Chudnovsky, Edwards, Kim, Scott, and Seymour to prove the conjecture. This result tells you how to find the other 2 dijoins in the remaining graph. So this Barnett type conjecture implies Waddell's conjecture for the planar case with tau equals 3. And with that, I will conclude my talk. Thank you.
Awesome. Thank you so much, Ahmad. Let's do a round of applause. If you could please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3.
Thank you very much, and I apologize for going over.
Oh, that's okay. Do we have time maybe for a quick question? If anyone wants to jump in?
Yeah, I was wondering if there might be a nice remedy to Edmonds-Giles conjecture. Is there a nice sort of, do you think that the obstruction might sort of, it comes up everywhere, right? I mean, you're always seeing the same thing. Do you think there might be a result that sort of somehow says that it's really at the core of all the counterexamples?
So are you asking for a characteristic feature of all the counter examples to Edmonds-Giles?
Somehow, so that you're always somehow looking at Scriver's counterexample.
Yes. Scriver's counterexample. So this is actually where strong base orderability comes in. There's a few reasons why Scriver's counterexample shows up. There's a few aspects of the problem, and this one aspect of it was looked at by Chudnovsky et al., where they said, well, one problem this has is that the solid edges don't form a connected graph. So they form disjoint. So this was the aspect they looked at.
There are a lot of things where you do that sort of thing, but I was wondering if there might be like a sort of like a well, you know, there's various things where you say that this is a minor of that, and like it's not really clear what it would be, but I mean, I'm just wondering.
So it is. So I tell you, the problem with Scriver's counterexample is K4. So this is the aspect that we've picked up. So there's two aspects. One aspect is this row parameter, which ends up being 3. And why does that matter? This row parameter that shows up is the rank of these matroids. All of these matroids that like M0 and M1, these all have rank 3 in Scriver's example. And what's happening is that as soon as the rank is at least 3, matroids of rank at most 2 are strongly base orderable. Whereas as soon as the rank goes above 2, it's at least 3. Now K4 shows up, the cycle matroid of K4, and that's not strongly base orderable. And so that's what's happening in Scriver's example, and also in our example over here. It's the basically the cycle matroid of K4 shows up as a minor. And this is what we do in stage 4. We try to actually exclude this minor. And so for Scriver's example, we show a different way to find the dijoins. So that's one aspect of it. So that's one reason why Scriver's example is so important. That's one aspect. There's another aspect, and we don't address it in the paper, but we spent many months on it, and it's still a plausible way. The other aspect is cuboids. Scriver's counterexample basically embeds this cuboid, which is basically it corresponds to this object coming from the unit hypercube that satisfies nice geometric properties. You have a nice description, polyhedral description for it, but the point set itself is not nice. So the hyperplanes describing the set are very nice, but the vertices inside the set don't behave nicely. They don't have nice packing properties. And that's another thing that's exemplified in Scriver's example. And actually what you can do, if you take that point of view, you can actually characterize Scriver's counterexample. And there's actually a whole family of counterexamples that look like Scriver's counterexample that you can characterize it. We don't do this in the paper, but we've done it. But it requires a lot more machinery. But yeah, there's several aspects to it. So there's these two, and then there's the aspect by Chudnovsky et al.